Hello, ladies and gentlemen. I'm Mr. Zebe, and today I'll be teaching you on how to test for linearly independence and dependence on vector spaces. Without any further ado, let's get into the content. So we already know that a vector, it is a physical quantity that has both magnitude and a direction, and then it is represented by an arrow at the top. So from that statement, we can actually deduce that or make a conclusion that every collection of vectors is either linearly dependent or linearly independent. So we have to let vector v1, vector v2, all the way to vector vn, which exist in the sample space V. This means that vector v1, vector v2, all the way to n are actually the subset of the vector space of V. So for linearly independence, there exist two conditions. This sign means that there exist, it is an existential quantifier. So there exist two conditions. So the first condition says that all the scalars should be equals to 0. So my scalar on this case will be represented by A. So if we take a scalar and multiply it by its respective vector 1, a scalar 1 and a vector 1, if we multiply them together and then we add a second scalar and a vector 2 and then a third all the way to an nth scalar multiplied by a vector scalar, we are saying that their summation should give us 0. So you can write it this way, or you can choose to use sigma notation. So on sigma notation, it says that the summation of the product of a scalar ai and a vector vi from I equals to 1 all the way to n. So the second condition says that all the scalars are equal. So the first scalar is equal to the second scalar and the third scalar all the way to the nth scalar. But they all equals to 0. This means that a first scalar will be 0 and a second scalar will be 0 and then an nth scalar should also be 0 so that it can be linearly independent. So for linearly independent, it takes these two conditions. So if it gives us 0, we know that the solution will be trivial. But for linearly dependence, we say that vectors are linearly dependent if the equation has a solution when at least one of them is not equals to 0. So if this equation has at least one scalar which is not equals to 0, then this cannot be linearly independent, so it will be linearly dependent. So what do we mean about that? We mean that a scalar 1 is not equals to scalar number 2, and then sometimes a scalar number 1 can be equals to scalar number 2, but you will see that a scalar number 2 will not be equal to scalar number 3. So and then all the scalars won't be equal to the nth scalar, and then they are all not equals to 0. So the solution would be non-trivial. So the solution would be non-trivial as is not equal to 0. So we will also use a row echelon form to actually compute those matrices in order for us to test for linearly independence and linearly dependence. So right now we can just take an example. Suppose that we are given three vector spaces, respectively VA, which consists of the vectors 1, 2, and 3. And then we are also given another vector space of VB, which consists of the vectors 3, minus 2, and 1. And we also given VC, which consists of a vector 1, minus 6, and also 5, respectively. and also 5 respectively. So, but what did we say about this kind of statement? They are asking us to test for linear independence and linearly dependence. But we can see that this problem is actually in 3 dimension. It's actually in 3 dimension. So what can we do about this one? But we know that the summation of AI multiplied by VI equals to 0 from I equals to 1 all the way to N. And what do we mean about that? We mean that we can actually expand this equation so that we get so that we get A1 multiplied by V1 plus A2 multiplied by V2 plus A3 multiplied by vector number 3, and we say that their summation should give us 0. Their summation should give us 0. So if we take this scalar and we multiply by this vector, we are going to get 1 here. We are going to get A1 because of it is just A1. So we are going to add. So if we take this scalar number 2 and multiply this 3, we are going to have 3A2. And then we add the third scalar. So if we take the third scalar and multiply it by this one here, we are going to get A3, which is just equals to 0. So this is the first row. So we are going to the second row. If we take the first scalar and we multiply it by 2, we get 2A1 plus. If we take the second scalar and we multiply it by this vector, we will get minus 2A2. And then we add. So if we take this the third scalar and multiply it by this one, we will get minus 6A2. All equals to 0. Third row. If we take the first scalar and we multiply by this 3, we'll get 3A. I'm sure now you are seeing the pattern. And then we take this one here, and then we multiply it also by a scalar A2. So it will just be A2 because of its 1. This one is 1, guys. Forgive my handwriting. So if we take the scalar number 3 and we multiply it by 5, we will get 5A3, and then it's all equals to 0. So this thing can be written in a form of a matrix. And then my matrix, I will call it matrix A. But you can choose any variable. This is my matrix. So I'm only going to take the coefficient of the first row, which is 1, this one here, 3, and this one again. And then this one equals to 0. I'm going to take this 2 again. And here I'm going to take this minus 2. And here I'm going to take this minus 6. And here I'm going to take 3. And here I'm going to take 1 and 5. This equals to 0 is this one. And then even this one equals to 0. It is our augmented matrix. But this matrix can be written in terms of a row echelon form. But what is a row echelon form? A row echelon form, it is a matrix like this. This is a matrix in a row echelon form. So, what can we do there to achieve a row echelon form? We can target this stream and try to convert it to 0. Or we can try to convert this to 0. But let us start with this stream so that we can have this version of a matrix. Let me write my matrix here, my matrix A, so that I can erase it. And and 5, and here it will be 0 and 0, so that I can erase it here. So right now, let's target this tray. How can we make this tray 0? But if we take minus 3 and we multiply it by row 1, and then we add it to row 3, then on this entry, on the third entry, we must get 0. So guys, remember that I'm adding this row 1 to row 3. So the only row that will be changing will be row 1. It will be only row 3. But row 1 and row 2 will remain the same. They will never change. So right now, let's write our matrix like we see it. Is 1, 3, 1. This one equals to 0. I said row 1 will not change. And also row 2 will not change because of I'm adding to row 3. So row 3 is the one that will change in this case. So guys, you can take a look at this. So if I substitute this one here, and then I also add by this 3 here, I'm getting 0. That's where this 0 will stay. So I can substitute this 3 and this 1 here. So if I substitute this 3 here and I substitute 1 here, how much do I get? I get minus 8. So that's where I'm going to have minus 8. So if I substitute this 1 and 5, here, what do I get? I will get 2. That's why here I'm getting 2. So here, actually, I have achieved this 0. Right now, I have this 0. But I can convert something again so that I get 0. So let me target this 2 this time around and change it and make it 0. So, but if we can check row 1 and we say minus 2 and we multiply it by row 1 and we add it to row 2, on this entry we'll get 0. But remember guys, I'm adding to row 2. So row 2 is the only one that will be changing. But row 1 and row 3 will remain the same. They will never change. So let me write that matrix. So like I said, row 1 and row 3 will never change. Sorry guys, this is equals to 0. Even if you don't write these things down, no problem, as long as you know what you'll do in the end. So let me substitute this 1 and this 2 here. If I substitute 1 here and I add by 2, I'm getting 0. So this is the 0 that we wanted to achieve. But when we are doing for these 2, we must also do for all the rows. So let me substitute this 3 here and add by minus 2. How much do I get? I get minus 8. And that is minus 8 that I'm getting. It's here. But if I substitute this 1 and this minus 6 on this equation, I'm still getting minus 8. And this will be our minus 8. This is equal to 0. Sorry guys. This is equals to 0. Let me erase this part. Actually. So I'm getting 0. So what can I do now? Actually, I can try to make this 1. I can try to achieve this to be 1 and also achieve this to be 1 according to my matrix, because if I do this one and this one, it will be a little bit difficult to compute. So I can say row number 2, all of it, I will multiply it by minus 1 over 8. And then row 3, because I want to achieve this one here. And then row 3, I will multiply it by 1 over 2. So if I do that, row 1 doesn't change, guys, because of I'm not doing anything on it. So I will have 1, 3, 1, 0. But if I multiply 0 by minus 1 over 8, I'm getting 0. This one I'm going to get 1. And even here I'm going to get 1 when I multiply by minus 1 over 8. But if I multiply by 1 over 2 here, I'm getting 0. And here, I will get minus 4. And here, I will get 1. So, this is the matrix that we are having right now. This equals to 0 and this one equals to 0. So, this is the matrix that we are having right now. Let me erase this part. So this matrix is nearly in row echelon form, this matrix. But what can I do to actually get 0 here? What can I do? I can try this again and again, but it will be just a waste of time. I can just multiply because of here I'm having scalar A1, scalar A2, and a scalar A3. So if I multiply by this scalar, I'm going to get A1, A times this one, and 3A2 plus A3, it will be 0. Even on the second scalar, since it's on a row echelon form, let me remove this. So if I multiply this and this one, I'm getting 0 here. And then if I multiply this and this, I'm getting A2. Plus, if I multiply this and this, I'm getting A3. This is just 0. So, if I multiply this and this, I'm getting minus 4A2, because of this will be 0. And then A3 equals to 0. So, I can erase this part. But from this statement, we can see that A2 equals to minus A3. So I can substitute this into this one. So I can say minus 4, but what is A2? A2 is a minus A3 plus A3 equals to 0. This will give me 4A3 plus A3 equals to 0. So this is just 5A3 equals to 0. I can divide by 5 both sides. So my A3 will be 0. So since I'm having A3, I can come here and substitute this 0. So it will be minus 0 here. So my A2 is just 0. So since I'm having A2 and A3 to be zeros, I can come here and substitute. So when I substitute on that equation, my A1 will be just A1, but my A3 will be 3 times 0, but I'm sorry, my A2, and my A3 will just be 0, equals to 0. So we can see that A1 equals to 0 also. So that means that A1 equals to A2 equals to A3 and then equals to 0. This is the second condition. So since the second condition is met, we can say that this is linearly independent. And the solution is trivial. We can just take another example right now. I'm erasing now. So suppose that you are given a problem like this. They're given you a first vector space which is A and a second vector space which is B, and a third vector space in C, which is C. And then they're all in 3 dimensions. And they are telling you to us to test for linear independence and also independence. So the thing that we can do is that we know that the summation of AI times Vi equals to 0 from I equals to 0 all the way up to n. But this can be expanded to A1 V1 plus A2 V2 plus A3 V3 and is equals to 0. Is equals to 0 like that. But where we see V1, we can actually add this vector space. So it will be A1, and then this vector space, it consists of the vectors A, minus 2 and 0 respectively. So it's going to be minus 2, 0 plus A2, and then it consists of this, all of it. So it's going to be 4, 0, 8 plus A3, which is 3 minus 1 and 5. So this can be written in a form of an augmented matrix. I will call it matrix X. But this matrix is equal to 0. All of them is equal to 0. So if I can write this in an augmented matrix, it will be 1, 4, 3 equals to 0, minus 2, 0 and 1 equals to 0, 0, 8, 5 equals to 0. It's in the form of an augmented matrix, but this can be converted to row echelon form. So right now, since you already know row echelon form, we can see that we have already achieved 0 here. So we are not going to have much of a problem. But we can also see that we are already having 0 here. So it's going to be a little bit tricky to compute. But let's compute this anyways. Let's compute this anyways. So for us to change this to 0, let's target this minus 2. So we can say R1 plus R2. So check this. R2 is the one that has been added to. So it's the one that will be changing all the row. But R1 and R3 will remain the same. So our matrix X, if we do that, R1 will remain the same and R3 will remain the same also. But this part doesn't really matter. It will just give you 0. So if we do this, 2R1, so that we can get 0 here. So if we take this 2 and then we substitute this 1 here, and we add by this minus 2, we'll get 0. And that's where we'll place this 0. So if we add 4 here, if we add this 4 and this 0, so we are going to have 4, we are going to have 4 and we are going to have 0 here. So this will give us just 8. And this is where I will place my 8. So we can also do it for 3 and 2 and 1, So it will be 3 here and here is going to be 1. So it will be 1. It will be minus 1 here. Supposed to be minus 1. It's minus 2, which is this one, 0, and this minus 1. It's minus 1 here. So if we put minus 1 here, we will get 5. And then we already got 5. But for us to make this one 0 and this one 0, we can take row 2 and subtract it from row 3. So it's going to be, if we take row 2 and subtract row 3. So the row 3 is the one which will be changing because of it is the one which will be added to. But row 1 and row 2 will remain the same. This is the matrix that we got. This is the matrix that we got. Let me not erase it. So we'll have 1, 4, 3, and then here we are going to have 0, 8, 5, and this, don't forget guys, equals to 0. So if we take 0 and we subtract 0, we get 0, but 8 subtract 8 is 0, so we achieved this 0 here. But 5 minus 5 is just 0, so we are having another problem here. But this, we call them free variables. And they can be assigned to anything. You can assign, if you can check here, you can assign this 0, a1 to any variable that you want, but not 0, and even this one, and even this one, and even that one. So let me assign a2 to t, and say a2 equals to t. Yes, a2 equals to t. But remember, this is a1 here, a2 here, and then a3. So if we write these equations, we are having, if you can check here, we are having a1 plus 4a2 plus 3a3 equals to 0. And we are also having, this will be 0 here. So it's 8a2 plus 5a3 equals to 0. But a2 we have already assigned it to t. So where I see a2, I can just put at plus 5a3 equals to 0. So for me to solve for a3, I can see that 5a3 equals to minus 8t. So if I divide by 5 and I divide by 5, my a3 is actually minus 8 over 8t over 5. So I'm having a3 and I'm having a2. So I can just substitute a2 and a3 into this equation. So since I'm having a1, this is my a1, plus 4, but what is my a2? It's 4t, plus 3 minus 8 over 5. This is t. This will be 0. So if you can just press it on your calculator, you will realize that you will get something like minus 4 over 5. So this will be a1. So let me verify if I did the right thing. Yes, minus 4 over 5 equals to 0. But my a1 will be 4 over 5. But we can see that a1 is not equals to a2, and it's not equals to a3, and it's not equals to 0. So the solution is non-trivial. Linearly dependent. So